Hello, beautiful people, and welcome to the Chem Lab. Today, we're going to be looking at some multiple choice questions in preparation for the AP Chemistry exam, specifically Units 8.1 and 8.2, sort of the beginning of our unit on acids, bases, and buffers. So, in this video, we're going to be looking at recognizing strong acids and bases and calculating their pHs. We'll talk about the autoionization of water and what happens to the pH of pure water when the temperature changes. And we'll also look at a couple of questions that have reactions in them that affect the pH. So if all goes according to plan, in a few minutes you will have seen a whole bunch of multiple choice questions to help prepare you. And so let's get started. Let's start with some questions about recognizing strong acids and bases and calculating their pHs. We'll start with this one, which is a fairly straightforward question. Which of the following is a strong electrolyte in aqueous solution? And you get a series of choices. And when we see the term strong electrolyte, that means it is 100% ionized or dissociated. And so we're looking for a strong acid or base because those, by definition, are 100% ionized. And so I'm looking down this list. This is kind of just a recognition question. Hydrobromic acid is the only one in there, HBr, that is the strong acid. So that would be the strong electrolyte. All right, so once we recognize, and you should know your six strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. So have those in your memory so that you can recognize them right off the bat. And here we have perchloric acid in our next question. Which of the following statements about the pH of 0.01 molar perchloric acid is correct? So when you have a strong acid and you recognize it as strong, you can say it's 100% dissociated. So the molarity of the acid is also the molarity of the hydrogen ion or the hydronium ion. So that is the molarity of the hydrogen ion concentration. And if I take the negative log of that, I get a pH of 2. So that is my answer on that. Okay. Next question. At 25 degrees Celsius, aqueous solutions with a pH of 8 have a hydroxide ion concentration, OH minus, of, what is it? So what we need to do is say, all right, that's the pH. That's the negative log of the H plus concentration. And because we should know that the pH plus the pOH equals 14, okay, that means that the pOH of this solution is 6. All right, and then the hydroxide ion concentration is what happens when you take 10 and raise it to the negative 6. So that would be letter C on that. And by the way, if you need a refresher on pH and pOH, you can check out my Unit 8 playlist. There are several videos in there about pH and pOH, along with the review for the entire unit. So if you need to review those questions. Okay, the table contains information about 4 samples of 4 different monoprotic acids with the general formula HA. Great. They give us volumes, concentrations, pHs. Which statement correctly explains why the pH value of sample 3 is the greatest? Since pH is the negative log of the H plus concentration, right, that means it must have the smallest value of the H3O plus. And the rest of these are distractors. Again, you can pause the video at any time to read the question fully. I'm kind of trying to go quick here. So it has the smallest value of H3O plus. All right, so great. All right, a similar type of question in which they give us a whole bunch of data. Again, half of our battle on an AP chemistry exam is just getting through and dealing with all the information that's being given to us. All right, so the pH of 4 acids prepared at various concentrations are measured. The 4 acids are, in no particular order, chlorous, hydrochloric, lactic, and propanoic. Which of the 4 is hydrochloric? So again, we have to recognize hydrochloric is one of the 6 strong acids, so it's going to be 100% ionized. The rest of them are not, so that's our first thing. If we don't recognize that, we're kind of lost on this one. Okay, so then these concentrations are, if I'm looking for hydrochloric, and a concentration is 0.01, the negative log of 0.01 is 2. So that would give me its pH. And I'm looking across the list, and there's only one that has a pH of 2, and that is acid number 2. The rest of them have higher pHs, meaning they might have that concentration, but they're not as much ionized. So the pH is higher. Okay. So a couple of quick ones on mathematical expressions to finish this little segment off. Which of the following pairs of mathematical expressions can be used to correctly calculate the pH and pOH of 0.0015 molar KOH solution? Okay, so they don't need us to calculate it. They just want us to look at the expression. So first of all, the pOH is going to be the negative log. This is a strong base, by the way. Hydroxides of the alkali metals and sometimes barium and calcium are considered strong as well. So it's a strong base. The negative log of that is going to be the pOH. So I'm looking, there it is, and there it is. So these three are correct. This one is not. So I can immediately get rid of D as a choice. Then the pH is going to be 14 minus the negative log of that. So that works out to be letter C as my choice there. Again, if you need a refresher on those equations, check out some of my other videos with the content in it. And we'll do a pause the video moment here. So which of the following is the correct mathematical expression to use when calculating the pH of 0.1 molar barium hydroxide? Consider it to be a strong base. Have at it, and I'll see you back here in a couple seconds. All right, and if you picked letter D, then congratulations. So we want the pH, not the pOH. But we know that it's a 0.1 molar solution and there's 2 hydroxides per, so it's 0.2 moles per liter. Then the negative log of that would give you the pOH, which subtracting it, and it's going to be like subtracting a negative, gets you letter D from 14 to get the pH. In our next segment, we're going to be looking at some questions regarding the autoionization of water. And in my research, I've found that these types of questions occur really, really frequently. You can almost assume they're going to be on every single AP exam. And so these are pretty important. So let's get started with this one. The autoionization of water is presented by the equation above. So great. We've got the equation. Keep that in your mind. And also keep in mind that it is a 1-to-1 ratio. Water is constantly swapping protons with itself, producing hydroniums and hydroxides. But when this happens, it's an equal amount in pure water. So the temperature is going up, the pKw is going down. That's because as you go up to higher temperatures, the Ka value actually increases as well, and so you get more dissociation. So higher temp, more dissociation because it is an endothermic process. Again, that's covered in my review video. Based on the information above, which of the following statements is true? The dissociation of water is an exothermic process? Nope, we just said it's endothermic. pH of pure water is 7 at any temperature? No, it's actually not. The pH of water is only 7 under normal conditions at 25 degrees Celsius. As the temperature increases, the pH of pure water increases. So as the temperature increases, you're going to get more hydronium ion concentration, which actually results in a lower pH. So that is going to be letter D. It's kind of a tough concept to think it through. So we'll see a few examples from different angles in this segment. So which of the following accounts for the fact that the pH of pure water at 37 is actually lower than 7? That's because we're getting more hydroniums, and a negative log of that gives me a lower pH. So is it naturally acidic? Well, I mean, yes, but it's also naturally basic, so neutral in normal conditions. The autoionization constant for water, Kw, is greater than it is at 25 degrees Celsius, and there I see that that is my answer. Again, you can pause the video at any time to read the questions a little more thoroughly. All right, the value of Kw at 37 is 2.4 times 10 to the minus 14. Okay, so again, they're giving it to us at a different temperature. Which of the following statements about the pH and pOH of pure water is correct? This is a tricky one. All right. Is the pH going to be less than 7 and the pOH greater than 7, or any of these choices? Well, it turns out that we're going to get more dissociation, so more hydrogen ions, but also more hydroxide ions. And if you take the negative log of both of those two, because it's a 1-to-1 ratio, you'll get that the pH and the pOH are the same. They're not going to be 7, though, because we're getting more dissociation. It's going to be less than 7 for both of those. Okay. Another way of saying the same thing. In fact, let's take a look at this one. This will be our pause the video moment for this segment. In pure water, some of the molecules ionize according to that equation. And which of the following mathematical relationships gives the pOH of pure water at 50 degrees Celsius? Take a moment, pause the video, and I'll see you back here in a second. All right. Lots of these look really good, but you got to laser focus and know that in pure water, the pOH and the pH are going to be the same. They might not be 7, but they'll be the same. Okay. So the value of Kw for water at 0, okay, now we're getting colder than room temperature, is actually less than it would be at room temperature. What's the pOH of water? So we can help narrow it down, because if we're at a lower temperature, we'll get less ionization and a higher pOH than 7. So that narrows it down to these two. And if I do the math and basically take this and solve for x squared, well, set that equal to x squared, 1x for the hydronium, 1 for the hydroxide, and take the square root of that, take the negative log, and I get 7.5 on that. All right, another quick pause the video moment. Value of Kw at 40 is 3 times 10 to the minus 14th. What's the pH of pure water at 40? Take a moment, pause the video, and see if you can get this one. All right, and if you recognize that because we're at a higher temperature, the pH is going to be lower than 7, not that low, but you might have calculated a 6.8 on that. See how frequently these questions come? All right, and the last one is a longer one, so I saved it for the end. In pure water, some of the molecules ionize according to that same equation. That's great. The extent of the ionization increases with temperature, and that's what happens to the pH as you increase the temperature. Now, if you laser focus and remember that the pH and the pOH do the same thing in neutral solutions, which of the following represents the variations in pOH under the same conditions? So note, we're starting at a hair over 7.2 and falling down to just under 6.4. And if you look at our 4 choices, we can see that part A also starts at the same location and ends at the same location for pOH. And so PA is correct. You can take a moment and look at the other samples if you would like to see what they're doing with them. Next, let's take a look at a couple of more tricky ones dealing with molarity and pH. Starting with this one. A student mixes 100 milliliters of 0.25 molar HCl and 200 milliliters of 0.5 molar HClO4, and then dilutes the mixture with distilled water to a total volume of 500. The H3O plus in the final concentration is closest to. Okay, this is the type of question my students often get a little bit carried away with because there's a lot going on. But again, it's one of those laser focus situations. First things first, this is going to produce hydrogens. That's going to produce hydrogens to make those hydronium ions. And we want to know the total molarity at the end. Okay, so I need to recognize they're both strong acids, so they're going to 100% ionize. And then dilute it at the end. So there's a lot going on here, but watch what I did with the solution. All right, I got an answer of letter C, because it's important to note, this is how you address this kind of question. Yes, this is going to produce hydrogens, that's going to produce hydrogens, but once they're produced, those hydrogens are now independent of where they came from. They're all swimming around in the solution all together. They don't care if they came from a chlorine or a perchlorate ion. They're just all swimming around. And then they're all in the same volume. So what really matters is the total moles divided by the total liters at the end, whenever you're going to measure it. So I first calculated volume times molarity of the first one to get that many moles of protons. That volume times that molarity to get that many moles. Total moles, I just added them up, divide by the volume that they're in, and I get back to 0.25 moles per liter on that. All right. Here's a quick dilution question. How can 100 milliliters of sodium hydroxide solution with a pH of 13 be converted to a sodium hydroxide with a pH of 12? Okay, so we're going to add water to this, and as we do it, the concentration of OH is going to go down, and therefore the pH is also going to go down. The question is, how much? Okay, and the key is we have to remember that the pH or the pOH is the negative log, and it's log base 10. So every change in one pH value results in a tenfold increase or decrease in the concentration. So it's not doubling, it's not just proportional or anything, it's tenfold. So basically, if I want to get the pH to go down by 1, I have to reduce the molarity by 10 to 1/10 of its original molarity, which is also done by making the volume 10 times as big. So V1M1 equals V2M2. The dilution equation gets us that answer. Okay. Take a look at this one. This is all about a titration. Maybe you've done titrations already, and if not, you're going to get into them and have to recognize a graph, something like this. To determine the concentration of NaOH solution, a student titrated 50 milliliters with 0.1 molar HCl. We get a graph that looks something like this, typical of a strong base, strong acid titration. One student titrated the NaOH with 1 molar HCl instead of 0.1 molar HCl. How would the student's titration curve differ from the original curve? All right, first of all, I want to sketch what it's going to look like. It's going to start at the same amount, but we are actually going to get to the equivalence point 10 times faster. So it's going to drop really quickly and start going and going and going. And so what we end up with is also it's going to end up lower because we have a stronger acid in excess at the end of it. So the correct choice in here is that they're talking in C and D about the pH far beyond the equivalence point is actually going to be lower than in the original curve for that one. So hopefully you would choose letter D. We'll finish off this episode with 3 questions on the chemical reactions and how they might change the pH. The first one I'll do together with you, and then we'll do a couple of pause the video moments to see where you're at. Okay, look at the first reaction. 2 potassiums in water makes potassium hydroxide and hydrogen. It's an excellent reaction. It's super awesome. You can check out my video on alkali metals for that one. When 3.9 grams of potassium, I recognize that as being 1/10 of the molar mass of potassium, so 1/10 of a mole, is added to 200 milliliters of water. All the K reacts and is represented by the equation above. What's true about the pH? Well, because we're producing hydroxides, the pH is going to go up. We're going to make the solution more basic, and we'll end up with a pH that is greater than 7. All right, our next pause the video moment. If you want to pause the video and read this question, this is about a redox reaction between hydrogen peroxide and permanganate. And we want to know which of the following best describes what happens to the pH of the solution as the titration proceeds. So take a moment, pause the video, and see if you can predict what happens to the titration. And if you chose letter C, as we add this reaction along, those are going to be consumed as part of the redox process. And so the hydrogen ion concentration, we will get a solution that is less acidic, and the pH is going to increase. So congratulations if you got that one. And one last pause the video moment. When a 0.64 gram sample, again 1/10 of a moles of that, is added to 100 milliliters of water, all of the calcium carbide reacts with water as represented by this equation. At the completion of the reaction, the pH is found to be above 7. Why? Take a moment, pause the video, and see if you can get that one. All right. And we must have some, if it's above 7, it must have some OH present in solution. And the only place that comes from is there, which means the calcium hydroxide must be slightly soluble in water. So there you have it, a bunch of multiple choice questions on 8.1 and 8.2. Hope you found them helpful. If you have any questions, you can send them to me. In the meantime, happy studying and have a great day.